Hello, everyone, and welcome to today's webinar. My name is Patrick Hawkins. I'm a design engineer in the Thorlabs Advanced Photonics division, and I'll be moderating today's talk. Today's presentation is Optical Fiber 101, Translating Theory to Practice, and will be given by our very own Dave Gardner. David Gardner is a senior process engineer for optical fiber here at Thorlabs. He's approaching his 10th anniversary with Thorlabs, and Dave leads the development and production of our fluoride optical fiber, while also supporting the characterization, testing, and R&D developments for our silica and fluoride fiber manufacturing teams. Dave plays a major role in the development of new fiber products and processes here at Thorlabs. During this talk, Dave will be discussing the core concepts behind fiber technology, examples of different fiber types and their applications, and how fiber is manufactured here at Thorlabs. I've known Dave for just about the entirety of my 8 years with the company, during which I've always enjoyed working together on new fiber products, new metrology setups, and test processes. So I'm very much looking forward to Dave's presentation. We're accepting questions throughout the entire event. To submit questions, just click the Q&A button at the top of the screen, and Dave will address those at the end of the talk. Okay, I'll turn it over to Dave now for Optical Fiber 101.
Thanks, Pat. Thanks everyone that's joining us today for this webinar. I'm Dave, and we'll get right into it. Here's a little agenda of what we're going to discuss today. We'll start off with some basic info on optical fibers and how they function. Give a little info on how we manufacture optical fibers, a rundown of common specialty fiber types, some usage tips for using fibers in your lab or in your application, and then finally a little bit of information about the fiber manufacturing that we do here at Thorlabs. So, starting at the beginning, you may have seen this from an intro to physics class, the concept of total internal reflection. This occurs when we have a critical angle that is greater than a certain value as measured from the normal. Below this value, we have refraction as per Snell's law. But at the critical angle or above, we have total internal reflection, which importantly means 100% of the light is reflected at this interface between two materials with different refractive indices. Common example would be water and air or glass and air. But in an optical fiber, the way this works is we have two different layers of glass. And these two layers of glass have a slightly different refractive index. It's a pretty small change, typically on the order of like 1% or even less. And what this means is that the critical angle is large, or in other words, the light has to be incident on this, this boundary at a pretty shallow angle to experience total internal reflection. But this is the basic structure of an optical fiber, the inner layer being called the core, the outer layer being called the cladding. And this functions as essentially a cylindrical waveguide. Taking this waveguide concept, we can define one of the really fundamental specs of a fiber, which we call numerical aperture, or NA. You may hear this word in the microscopy world to talk about objectives and lenses and different things, but in the fiber world, really what it is it's a measure of the index difference between the core and the cladding, or a measure of the critical angle. And you can see the equation there right here. And it really defines the cone of light, so to speak, that can be coupled into and guided within a fiber. So a larger NA means that the acceptance angle of the fiber is larger. It means there's more light collecting ability of the fiber. And then once the light's inside the fiber, it means stronger light guidance. You can see some common fiber NAs and the resulting angle of acceptance. And then what I think is a pretty neat image here under a microscope. We're just looking at a fiber with light exiting, blue light, at about 0.17 NA. Taking this basic fiber waveguide structure, we can define the most basic and the original type of optical fiber, what we call a multimode fiber. So we can think about this two ways. Using ray theory, the idea is that light can follow multiple paths along the fiber. You know, can be at the critical angle or below the critical angle, or a shallower angle, I should say, and will still be guided. So we can have multiple paths throughout the fiber. Thinking about it from a wave theory point of view, another way to say it is we launch light into the fiber, it's going to excite a superposition of different waveguide modes, and there'll be a certain intensity distribution between those modes, and also each mode has a different spatial intensity distribution. The diagram here shows some of the lower order modes. But in short, the multimode fiber can support multiple modes. If the fiber is bent, this angle of incidence on this core cloud interface will change. And therefore, if you bend the fiber, the modal distribution will change along the length. And the output pattern, of course, at the end of the fiber will change as the fiber is bent or manipulated. Also importantly, modes with high angles of incidence at that core cloud interface can be lost if the fiber is bent or if the fiber is bent too much. And from a telecom point of view, telecom is a common application for fiber, sending data down a fiber in pulses. Multimode fibers have what we call intermodal dispersion. What's basically the idea is that different modes follow a different path length. So if we send a pulse of light through the fiber, that pulse is going to be distorted in time as it goes along the fiber. It's going to be spread out or smeared. So that limits the data bandwidth that can go through multimode fibers. And then the other type of fiber, which is pretty common, is what we call a single mode fiber. So basically a single mode fiber is where we've taken this core clad structure and we've tweaked the design to make the core pretty small relative to the wavelength of the guided light. The core diameter is going to be a couple wavelengths in diameter. And because of this, only this fundamental LP01 mode is guided within the fiber. Now, a given fiber design, so a given core diameter and NA, we're only going to see single mode operation within a certain wavelength range. There's one wavelength called the cutoff wavelength. This is the shortest wavelength where the fiber supports single mode operation. As we make the wavelength smaller, if we keep the core size constant, eventually more than one mode can, so to speak, fit inside the core. And so at wavelengths shorter than the cutoff wavelength, the fiber operates as a multimode fiber. And then similarly, if the wavelength gets too long, it kind of doesn't fit in the core anymore, so to speak. And so at long lengths, the fiber won't guide light anymore. We call that the bend edge. It's like the region where the wavelength range where the fiber no longer guides light. So just as an example, a very common telecom fiber design will have an 8.2 micron diameter core, a 0.14 NA, and that supports single mode operation in the 1260 to 1625 nanometer range. Right here we see some cross sections of fibers, single mode fiber versus multi-mode fiber. You can see the core is much smaller. And single mode fibers have some interesting properties. Only light with an m² value pretty close to 1 can be coupled into the fiber, so it's hard to get the light in. But once that light's in there, the output pattern is Gaussian, and it remains constant as the fiber is bent. So the single mode is pretty bend insensitive. There's also no intermodal dispersion since there's one mode, so the bandwidth, the data bandwidth on these fibers can be much higher. So that's an overview of basic fiber design. So now I'm going to shift gears a little bit and talk about how do we make these fibers, a little bit about fiber manufacturing. It all starts with the glass that we're going to make the core and the cladding out of. Typically we use silica glass or silicon dioxide, and this glass has to be extraordinarily pure, more pure than nearly all other applications glass is used for in the world. Really, the long and short of it is the path length through the glass in optical fibers is very long. And an example I like to give is if you've ever been in a building with older windows, you may see a greenish tint in the glass. windows are going to be a couple millimeters or a centimeter thick. And that greenish tint is due to some iron oxide contamination within the glass, trace amounts. Now, for a window, that's fine, no big deal. Even for something like a lens or a scientific window that you might use in an optical setup, the optic's only going to be a few millimeters thick, so trace absorptions might be okay. But in a fiber, the whole length is glass. So it's almost like looking through a window that's 100 meters thick, let's say. And so trace absorptions become very, very important. Trace metals and also water absorption due to the OH bond are major concerns. So we take great pains to make sure that the glass used to make fiber is very pure. In the top right corner here, this graph is showing absorption or attenuation versus wavelength for a fiber, and all of these peaks are due to water absorption, just as an example. The other important thing for the glass used to make the fiber is we need an index difference between the core and the cladding. And there's two main strategies to achieve this. Sometimes, depending on the application, we may dope the core glass with germanium oxide, which raises the index. Or alternatively, we can use a pure silica glass core and fluorine dope the cladding to lower the index. Either way, we get an index difference, so we get light guidance. And we take these two glasses and we make what we call a preform. Preform is basically like a giant version of the fiber, something like 10 to 100 millimeters in diameter, most commonly about 25 millimeters in diameter, and up to several meters long. So a big glass rod, and it has the core clad structure built in. And from there, we take the preform and we turn it into fiber. Now, how do we do that? This process would be called the fiber draw process. So we take this preform and we heat a section of it until the glass begins to soften, and that's in the neighborhood of like 2000 degrees C. While the glass is soft, we pull it in a very careful way, and this has the effect of basically shrinking the preform and stretching it out. So we take this core clad geometry and we stretch the fiber, so we shrink that geometry while still maintaining the same core clad relationship, still maintaining that core clad interface and all the structure that we need to function as a waveguide. This is done on what's called a fiber draw tower, a little schematic of it here. So we feed the preform into this furnace at a constant rate. We have a laser micrometer that measures the fiber diameter and a capstan wheel that pulls the fiber. And those are controlled with an active feedback loop so that we pull at the right speed so that we get the right fiber diameter. It's kind of like a volume in equals volume out sort of deal. And in this way, we sequentially stretch out the whole length of the preform. And amazingly, it's conservation of volume, but one typical preform, let's say 25 millimeters in diameter by 1 meter long, that can be stretched out into 40 kilometers of fiber at the typical fiber diameter of 125 microns. So the preform gets very long. And while we're doing this draw process, we also do add typically a UV curable plastic coating before the fiber gets to the capstan wheel that touches it. So that we apply that to the outer surface and we're left with an optical fiber. One common question that comes up when we're talking about fiber manufacturing or fibers in general is, how is this stuff flexible? I mean, it's made out of glass. How does that work? And the answer to that is, yeah, first of all, if you've ever handled fiber, it's incredible. You can wrap it around your finger, it doesn't break, it's very strong. So glass as a material, silica, pure silica glass, has a very high theoretical tensile strength. In a fiber, when we're bending it, what ends up happening is the inside of the curve, the glass is in compression, and the outside of the curve, the glass is in tension. This is where a failure can occur. And this glass is inherently very strong, so it should be able to withstand a lot of tension or a lot of bending. However, glass is very sensitive to any kind of defect, any kind of thing, a stress riser, or anything that concentrates stress. That can cause crack propagation, ruining the glass's tensile strength and causing a break in the fiber. So basically what we're doing here with fiber is we are keeping the glass as much as we can 100% free of internal and external defects. so that we preserve that inherent tensile strength. Some of the things we do are we make the preform out of ultra-pure glass, so there are no internal defects, no internal stress risers. We very carefully clean the preform surface to make sure it's pristine before the draw. That draw furnace where we heat the preform is kept purged with extremely pure inert gas. The surface of the fiber as it comes out of the furnace is kept clean on the draw tower. And we immediately put that UV curable or other plastic coating on. And that's why that's on the draw line, is so that we cover up that perfect surface immediately and preserve it. And in this way, we're able to create a glass fiber that's very, very flexible. The coating is what preserves the strength, but it does have some downsides as well. So one of the main ones is that this coating on the fiber really dictates the operating temperature range of the fiber. So if the fiber is going to be used in a hot environment, the coating is what fails first. As I mentioned, the silica glass is taken to something like 2000 C or above, and it can remain stable up to maybe like 1500 C or above. You can still have that waveguide's going to function. There's not going to be any major issues. However, the coating that we put on is going to only work at a much narrower temperature window. The most common coating would be like a UV curable acrylate. Here's a fiber cross section. This is a multi-mode fiber where we're showing the core and the cladding and a layer of acrylate coating around it. This really will work up to about 80 C. There are some high temperature acrylates that can get to 100 or 120 C. So of course, for any kind of lab environment, also a lot of telecom environments, room temperature, totally fine. High temperatures can have some issues. The next step up would be a polyimide plastic coating. That can go up in the neighborhood of 300 C and is used in things like oil and gas well sensors, aerospace applications. It's also pretty biocompatible, so it is used in some medical applications. And then go further, there are some metallic coatings available for fibers that can get up to the 400 to 600 C range. Those are much less common. I already mentioned it a little, but the coating can also determine sort of like the biocompatibility of the fiber as well, or the chemical resistance. And then also commonly, and not shown in my cross section here, but sometimes we'll extrude more layers on the fiber, what we call buffer layers, like Tefzel, Teflon, things like that, which function as additional mechanical protection, additional chemical protection, and things like that. Okay, so that is an overview of how we make the fiber. And with that knowledge in hand, we can talk about common specs for fibers. If you're picking out a fiber for your application, if you are trying to figure out what a fiber can do for an application, here are some key specs. There are some common specs, and then there are some that apply specifically to multi-mode or single mode fibers. So some key specs for all fibers. First and foremost, the attenuation, typically measured in dBs per kilometer of fiber. How well does the fiber guide light? How much light is lost over a length of fiber? That's typically specified at a wavelength or over a wavelength range. There's something called the proof test level. And what we do here during manufacturing is we subject every point along the length of the fiber to a certain stress, thereby proving that the fiber is at least a certain amount strong without, of course, breaking the fiber. So this is a measure of the fiber's mechanical strength. There's the minimum bend radius, which is specified by the manufacturer to encompass where the waveguide will function as you bend the fiber, and also how much stress the fiber can be under before we could have some mechanical issues. And then, of course, like I just mentioned, the coating material is going to dictate the operating temperature range of the fiber, as well as biocompatibility, chemical resistance. For multi-mode fibers, importantly, we have the core diameter and the Na, which really defines the waveguide of the fiber. And additionally, what we call the hydroxyl ion or OH content. Fibers are typically called low OH or high OH. And this is really for multi-mode fibers what determines the operating wavelength range. As we see in the example here, this is an attenuation curve for a high OH fiber and a low OH fiber. As you can see, of course, the high OH fiber has more water absorption peaks, but there is an advantage, which is in the visible. It can have lower attenuation. The low OH fiber is the clear winner in the near IR. And so commonly multimode fibers are specified, high OH for visible, low OH for near IR. On the flip side, for single mode fibers, we have the single mode operating wavelength range. So typically the way it works here is the fiber designers have taken care of choosing an appropriate core diameter in NA to give us this single mode operating wavelength range, like I mentioned earlier. Of course, typically they may specify the operating wavelength range and or just the cutoff wavelength, which is going to be the shortest wavelength where the fiber is truly single mode. And then in addition, what's called the mode field diameter. You can think of this as the effective core size. In a single mode fiber, as I mentioned, the core is pretty small relative to the wavelength. And so that LP01 mode ends up actually traveling in a region slightly larger than the core. Mode field diameter is a measure of that region in the fiber where the light is guided. And so it's typically a bit larger than the core size. And that's really, it functions as the effective core size for the single mode fiber. So hopefully with these specs in mind, if you're ever picking out a fiber for an application, things will make sense. And next we'll move on. The next part of the presentation, we'll talk about common applications for fibers and also some interesting specialty fiber types beyond the standard single mode and multi-mode. So in the world, optical fibers are used obviously for a lot of applications, but really telecom is the main one, is a very large part of the market. By telecom, I mean transmitting telephone, internet, other data signals within data centers, data center to data center, out to customers, even undersea cables that link the continents, all use optical fiber. And that's such a big part of the market that it commonly breaks down into telecom and like everything else. And everything else we call specialty fibers, because telecom is, again, so dominant. Some interesting applications in the specialty fiber world would be spectroscopy, sensors, imaging, light delivery, even active fibers where we have a laser gain medium embedded into the fiber. Now, how does this sit with our whole single mode versus multi-mode breakdown? Single mode is used, first of all, for what we call long haul telecom. So that would be, again, undersea cables running thousands of miles or kilometers from continent to continent, things like that. Also, it's used for certain sensors and certain fiber laser applications. And really, multi-mode is used for nearly everything else. That includes short haul telecom and a large number of specialty applications. So beyond single mode and multi-mode, here's a summary of some interesting other fiber types. So one common fiber type is what we call PM single mode, or polarization maintaining single mode fiber. What we do here is there are the fiber design is made such that there is stress-induced birefringence in the core. That can be due to something like stress rods embedded in the cladding. It can also be made with by making the core elliptical, different strategies like that. But however we do it, the idea is the fiber now has birefringence. It has a fast and a slow axis, and light that's input that's coupled into the fiber with linear polarization. That linear polarization is maintained through the fiber, even as the fiber is bent and manipulated. Another interesting fiber type is what we call graded index multimode fiber. Now, everything I've shown you so far is what we would call step index fiber. So in other words, there's a step change in the index between the core and the cladding at that core clad interface. Instead, in these graded index fibers, we have a radial index gradient. which replaces that step index. And how cool is this? Light actually travels in a curve inside this fiber along this index gradient. These multimode fibers are commonly used in, one example would be telecom applications, because this graded index design can reduce intermodal dispersion. So you can get more data bandwidth through the fiber. So a lot of short haul telecom in data center, things like that can be graded index multimode fibers. Here's two more interesting fiber designs. One that we actually manufacture a great deal of here at Thorlabs is what we call polymer clad multimode fiber. And here what we've done is we've taken that core cladding coating structure and we've simplified it by using a low index polymer as both the cladding and the coating. So the fiber really only needs two layers. This second layer helps to create the waveguide, and it functions as that plastic coating to preserve the fiber's inherent strength. One advantage here is that these fibers can be lower cost. Another advantage is that we're able to make polymers with much lower indices than silica glass, and therefore you can get a bigger index difference between the core and the cladding, which means a higher NA. And there are fibers on the market up to and potentially above 0.7, which in the fiber world is crazy high. Taking the polymer idea a step further, we can make plastic optical fiber, where now we've replaced the core and the cladding with polymer. These are very low cost fibers. They're used for very short distance communications. Also, these are the fibers used in consumer electronics applications. For instance, to connect a TV to a stereo with an optical cable, that's going to be plastic optical fiber. They're very robust mechanically, which is great for a consumer environment. They're cheap. They do have pretty high attenuation though, compared to a glass fiber. And so they're really only useful in short length applications. Of course, these are notoriously also the fibers used in the classic fiber optic Christmas tree. And we'll take a turn from the very cheap fibers. The next slide is some very expensive fibers. So the first one on the top here is multi-core fibers or fiber bundles. So the idea here is it's many fiber cores bundled together. One way to make this is we draw out a normal fiber. We don't put coating on it. We cut those fibers and we stack them and make a new preform and then draw that. And the claddings all melt together and you get a fiber with a multi-core structure. Another way would be the fibers can simply be epoxied or glued together. But the idea here is we create a fiber with many cores, and we can also create, this can be much larger diameter than a single glass fiber while still remaining flexible. So a classic example of an application for this is an endoscope, because you can image onto one end of this fiber and then see the image on the other end. And another interesting application is just to create a very large yet flexible fiber, which can be used for instance, high intensity illumination applications. And then I'm going to say it's the most expensive of all of the classic fibers. It's going to be what we call a photonic crystal fiber. There's no crystalline structure in this fiber. It's still made of amorphous glass. However, we use things like air holes or gas-filled holes in the design. So we get away from that traditional core cladding, two materials, two glasses with a different index design. What we're showing here is an example of a common photonic crystal fiber or PCF. And here we have what we call the core region, and then we have air holes or gas-filled holes. And we were able to create a waveguide with this structure. And there's many novel fiber designs possible in the PCF world. One example would be a fiber that's single mode over a much larger wavelength range than is possible with a typical fiber. Sometimes we call it an endlessly single mode fiber. These all PCF fibers, though, are very expensive and difficult to fabricate, but they can do pretty cool things. Next, we have active fibers or rare earth doped fibers. And the idea here is in addition to potentially doping the core with germanium oxide to change the index, we've also doped the core glass with a typically like a rare earth ion, which allows the core of the fiber to function as a gain medium for a laser. So pretty cool picture here. We have an erbium doped fiber pumped with 980 nanometer light, and it emits green. Looks very cool. And these are used to create in-fiber lasers, in-fiber amplifiers, and things like that. Commonly used in the active fiber world is something we call a dual clad fiber design. So the idea here is not only do we have a core and a cladding, but we have multiple claddings with successively lower indices, so that you can not only have light guidance at this core to first cladding interface, but first cladding to second cladding interface can also guide light. So we can build, for instance, something like a single mode fiber with a small core within a multi-mode fiber with a large core, and light can be guided within both of these layers. We can do this by having 3 layers or more of glass. We can also do it by having 2 layers of glass and combining that with a polymer cladding. These can be really useful. One example is pumping the doped core of a fiber. We can put the pump light into the cladding, and then it's gradually absorbed by the core. And another completely different application is for super high power fibers, where we're going to just put light into the core, but any light leakage is really important to be minimized, so the second cladding can guide light if any leaks out of the core. And next slide will conclude our tour of interesting fiber types, and I'll speak a little bit on alternative glass materials, another subject that's near and dear to us at Thorlabs as we manufacture some of this fiber. So the idea here is we're going to use glasses other than silica to make optical fiber, and from that we get a wider usable wavelength range. Silica fibers are useful in the UV. I'm going to say like 250 nanometers, 300 nanometers, depending on the fiber type, out to about 2.2 microns, and that's really what the material can support. Beyond this, we have multi-phonon absorption. Vibrational modes in the glass matrix are going to absorb the light. But if we use materials with lower energy vibrational modes, we can transmit further into the IR. And this basically means we're going to use a heavier glass host. Not only can that heavier glass host allow us to transmit further into the IR, it also can open up new laser lines with rare earth doping that would be quenched in the silica glass host. So one example is these heavy metal fluoride glasses. We actually manufacture a line of these at Thorlabs that I get to work on a lot, which is super cool. And these can work from the UV out to about 5 microns. This graph here is showing silica's transmission window versus 2 of our fluoride glass types. There's also germinate glasses, which can get you, like germanium oxide, can go from 1 to 3 microns. And there's chalcogenide glasses, which can transmit all the way out to like 10 microns. Last example here is a photo of a very highly erbium doped fluoride glass rod, and you can see the nice pink tint from the rare earth doping. Okay, so now we'll change gears to kind of the last main section of the presentation, which is talking about some usage tips. If you're using fiber in the lab or in your application, how do you do it? So the first thing to start with is fiber waveguide is great, but we got to get the light in and we got to get the light out in a good way. So pretty much required are optical quality end facets on the end of the fiber to get the light in and out. There's 2 main ways to achieve this. The first would be polishing. So very similar to how a lens is made. We're going to use successively finer grits of, for lack of a better term, sandpaper, very advanced sandpaper. And we're going to smooth out the end of the fiber until we achieve an optical quality surface. Typically, we glue the fiber into like a connector or a ferrule to this, like this example here. This is what we call an SMA connector, and you can see the fiber right there in the middle, which has been polished to an optical quality finish. And the other strategy is what we call cleaving, where we're going to actually exploit the tendency we mentioned earlier, the brittleness of the fiber, where if we have a stress riser or a defect, we can crack the fiber. To do this, we hold the fiber under a specific tension and intentionally create a defect, and that splits the fiber perpendicular to the optical axis and creates an optical quality smooth surface if done right. So those photos I showed you earlier, those microscope images of a fiber cross section, we prepared all of those through cleaving. Also this image here, which we're showing again, this is a cleaved end face, which is almost perpendicular to the fiber axis and is producing a nice beam out the end. In addition to polishing versus cleaving, there are also some special interesting end face treatments that can be used. For instance, we can angle the end face. That way any Fresnel reflections will not be coupled back into the fiber. We can add AR coatings for fiber to free space applications or other things like reflective coatings for certain applications. And when we're using these end faces, we need to be careful with them. The general guidance is really treat the end face of the fiber just like the surface of an optic. Give it all the same care. Use appropriate cleaning methods. And here at Thorlabs, we have tons of fiber inspection scopes, so we can look at those surfaces since they're so small and make sure that they're clean, not scratched, and ready to go. Once we have nice end faces, we can take it a step further and we can build the fiber into what we call a patch cable. So this is like a whole package where we have terminated, polished ends and then some sort of protective tubing in the middle. And the fiber is completely encapsulated and it makes it really easy to handle and work with. There are a variety of different connector types in the industry. Connectors that we call physical contact, so they're going to touch if you have two connectors mated together. Angled physical contact, connectors with an air gap where they don't touch. And the SMA connector is a common example of that. And then in between the connectors, we can have various types of mechanical protection for the fiber. Anything from simple plastic tubing up to reinforced tubing, all the way up to like a fully hermetically sealed shell around the fiber, depending on what application the fiber is going into. And one nice thing about having these convenient connectors is we can interconnect two different fiber devices or different cables together. That's what we call mating sleeves. This image here is showing the ferrule part, the end of the fiber that's polished out in what we call an FC-APC connector. So that's a fiber connector that has an angled physical contact. And these are the ferrules, and this is the mating sleeve that they're inserted into. The mating sleeve lines up the ferrules. You can see we have an angle, which is going to prevent Fresnel reflections from getting coupled back into the fiber. And the tips of the fiber are actually domed a little bit as per the FC-APC standards, so that the fiber cores are in physical contact, which again is going to reduce back reflections and enhance the coupling, reduce the loss between this fiber and this fiber. Mating sleeves are great, but you can't always go from fiber to fiber. Sometimes it has to be done free space to fiber, fiber to free space. So here we'll give a little data on how exactly do we get light into the fiber? How do we get it back out of the fiber? So coupling into the fiber it's really the same idea with single mode and multi-mode fiber. We use slightly different words just based on the different specs that these fibers typically come with. So for a multi-mode fiber, we're gonna use a lens to focus a beam of light onto the fiber core. And some general rules of thumb here are we want to fill no more than 70% of the fiber's core diameter and no more than 70% of the fiber's NA. The idea here is we're going to not launch higher order modes, very high order modes into the fiber, which would of course then be very bend sensitive, could fall out of the fiber if the fiber is bent. This also gives us some tolerances with mechanical positioning. If you're only at 70%, and your alignment is a little bit off, you're still going to get a good coupling efficiency. And of course, the beam of light and the lens and the fiber need to all be along the same optical axis. And we recommend fixing the lens, having the beam of light be normal to the lens and centered, and then moving the fiber linearly in X, Y, and Z to bring it the end facet right to the point where the light is focused. In single mode fibers, like I mentioned, it's kind of the same idea, but we say it a different way. We want to choose a lens that creates a Gaussian beam waist that is equal to or smaller than the fiber's mode field diameter. Of course, like I said before, the mode field diameter is a little bit bigger than the fiber core, but that is where the light's going to be guided in the fiber. And then we simply want the NA of the focus beam to be smaller than the fiber NA. Why don't we want to have it as 70% or less? The reason is when you're coupling into single mode fiber, the mechanical precision required is so much higher. So you're going to have the everything aligned and along the same optical axis, and therefore we can push the NA a bit higher and still get good coupling efficiency. We're also not worried about coupling in higher order modes that are going to be bend sensitive, since this fiber only supports one mode. So if we launch at the full NA, that fiber will, or that light will still be robustly guided within the fiber. And like I said, yeah, coupling into single mode fiber is no joke. It requires very high mechanical positioning, repeatability, and precision to get everything aligned correctly. The cores and the mode field diameters of these fibers are going to be on the order of 10 microns or less. And one final word about coupling is that, like I just said, fiber cores are very small diameter. There's not much surface area. And as we're focusing beams of light down to these small points, we can create very high power densities, even with relatively low power beams. And as we're aligning, if that light is not perfectly aligned to the fiber, it's pretty easy to actually burn the fiber end face from this high power light, especially if we're using a terminated fiber, a fiber that's been glued into a ferrule or a connector and polished out. Optical power levels as low as 500 milliwatts with single mode fibers, or maybe even lower, depending on the mode field diameter, can cause the fiber end face to burn. So it's something to definitely watch out for. The typical strategy is to align at low power, and then once everything's aligned, then turn up the optical power safely. Moving on from coupling, there is a way to avoid all of this altogether and keep your light in the fiber, and that is what we call splicing. Splicing would be an alternative to connectors and an alternative to free space coupling. The idea here, and by the way, I think this is a fascinating, amazing technology, is we can actually fuse the fibers together. We flat cleave two fibers, align the cores with great precision, and then weld them together. And what we create there is a nearly lossless splice. And we can even add more UV curable coating on top of this welded joint. And this connection is nearly lossless, and while not quite as strong as the original fiber, it's very strong. So this is a very useful thing for fiber in the lab. Splicing technology is incredible. On the same note as keeping the light in the fiber, there exists what we're going to call all fiber components or in-fiber components, where we can create complicated optical systems or optical circuits while keeping the light inside the fiber the whole way. I think the classic component in this example would be what we call a fiber coupler or a fiber splitter. The idea here is there's one or two input fibers, and then inside the coupler, two fiber cores are brought into close proximity to each other, thereby allowing some crosstalk or coupling of the light between the fiber cores. And in this way, we can split signals, we can combine signals, and it really works as an in-fiber beam splitter. So beam splitter would be the analogous optic in the free space optics world. And there are a number of other in-fiber components, and using them, you can build some really cool optical devices in fiber. this schematic here is of an erbium-doped fiber amplifier. And believe it or not, these erbium-doped fiber amplifiers are positioned every couple hundred kilometers along undersea fiber cables. They sit on the sea floor and they boost the signal, for lack of a better term, the internet signal, the data signal going through these fibers by amplifying the light using these components in a design similar to this. Okay, so that is my my last slide talking about the fiber world. I'm going to spend a few minutes here just talking to you about what we do at Thorlabs with regards to fiber, and then we'll open it up to questions. So here at Thorlabs, we are a manufacturer of step index specialty multimode fibers. We do that right here in Newton, New Jersey, which is where I'm talking to you from. Here's a picture of some of our draw towers, and we have a complete line of multimode fibers that are manufactured in-house. We also manufacture, in a completely vertically integrated way, fluoride glass fibers for the mid-IR. So we start with raw materials, make our own preforms, draw them into fiber. We characterize them, and we even make them into cables, all under one roof, again here in Newton, New Jersey. We make a full line, including multimode and single mode fibers with these fluoride glasses. In addition to the fibers we manufacture, we're also a reseller of a variety of other fiber types, telecom single mode fibers, specialty single mode fibers, and all sorts of other really interesting fiber types. Our catalog has a full line of fiber components. One highlight would be our patch cable assembly. We actually have a custom patch cable product line where you can design the patch cable on the website, and we'll ship it to you on the same day if it's ordered soon enough. In addition, we have a wide variety of different components that we sell. We have a full line through our Vytran office of what we call fiber processing equipment. So these would be like cleavers, splicers, and all sorts of other different ways to manipulate the fiber. And in addition to selling the equipment so that you can do it yourself, we also sell a line of products made with these fiber processing equipment, fusing fibers together, making a ball lens on the ends of the fiber, and a lot of other really neat applications. So thanks to everyone for listening to me. I hope you found this presentation informative. Hopefully it helps you with your future projects involving fiber. And at this point, I'll turn it back over to Pat.
Thanks, Dave. We have a handful of questions here. So I would like to start with something about the NA of fiber. This came in early on in the talk. Would the large acceptance angle correspond to a larger or wider divergence angle upon exiting the fiber?
Yeah, so that's exactly right. So that NA defines the acceptance angle into the fiber, and it also defines the angle, the output angle, for lack of a better term, at the end of the fiber. With one caveat, and that is that if you launch into a multimode fiber at a very small NA, much smaller than, let's say, the fiber is capable of supporting, and you only have a short length of fiber, call it 10 meters, let's say, just 1 meter, 10 meters, something like that, only some of the lower order modes may be excited. And so then what you get out of the other end of the fiber is probably going to only correspond to those lower order modes. There's not going to be enough time for bends in the fiber to sort of affect the modal distribution too much. And so you might see a small cone of light output from the fiber, smaller than what you'd expect from the fiber's NA. So it's a little bit the fiber design and the NA, and it's a little bit for multimode fibers what you put in.
Thanks. If you had a very short length of fiber, could you do something to make it to scramble the modes or something like that?
Yes, exactly. So that's something that comes up in applications sometimes. We want to make sure that we get, let's say we're using that fiber for illumination. We want to make sure we have that whole cone of light full NA of the fiber coming out the other end. We can use what you alluded to there, Pat, a mode scrambling setup. And the idea here is we purposely put some stress in the fiber. Two common ways are wrapping the fiber around, putting a lot of bends in the fiber, like wrap it around a cylinder. Or there's another device where it kind of has like teeth that the fiber would be in the middle, and it would mechanically stress the fiber. And in that way, we can purposefully excite some of those higher order modes. Of course, the third way is to just use a very long length of fiber. There's something in multimode fiber, a term called the equilibrium mode distribution. And the idea there is if you have a very long length of fiber with a random deployment, so random bends in it, and no matter what light you input in, what kind of modes you excite, eventually you'll end up with a mode distribution that's just inherent to the fiber from natural mode scrambling or from purposeful mode scrambling. And so the idea when we mode scramble is we want to get to that equilibrium mode distribution through artificial means.
Gotcha. Okay, next one. What polymers do we use for our polymer clad or plastic optical fiber?
Yeah, so we have a few different polymers that we use in our polymer clad fibers. We have what we call our TEX coating, and that if you have a pure silica core, I'll actually go back to that slide. If you have a pure silica core and you have this TEX cladding, that produces a fiber with a 0.39 Na. Oh, it's many slides back. There we go. So if you have a pure silica core and a TEX cladding, you get a 0.39 Na. We also have a higher index cladding where if you have a pure silica core, you can get about a 0.5 Na from the core to the cladding. There's a trade-off there, which is that as you decrease the index of the polymer cladding, you make the Na higher, the polymer cladding becomes mechanically weaker and less robust. So it's a trade-off. The higher Na polymer clad fibers are more mechanically fragile because that polymer cladding can be damaged more easily. And then the third type of sort of polymer clad fiber we make is we actually use a glass core and a glass cladding. And then we put the TEX coating on the outside. And so between the core and the first cladding, we have a 0.22 Na. And then from the first cladding to the polymer cladding, I don't remember offhand what that Na is, but those fibers are built for high power use. So you would launch light into the core and it's guided at the core clad interface. And if the fiber is bent too much or for whatever reason any light leaks out, it's then guided at that cladding to TEX coating interface. And so you get a second layer of waveguide. So those are some of the some examples of some of the polymer claddings that we actually offer in our products.
Cool, thanks. We had an interesting question come through. Basically for PhDs and postdocs, what would you say, what skill set or experience set would be helpful to move from academia to industry for people working with optical fiber?
Well, that's a big question. I'm not sure I have a great answer for that one. Certainly there are a lot of different jobs in the optical fiber world. Off the top of my head, there's people that do theoretical modeling of fiber designs and waveguides and can tell us, if we make the core a certain amount smaller and we decrease the cladding index by this much, then we'll get this favorable waveguide structure and this behavior that we're looking at for a certain application. So that would be, modeling, waveguide simulation, kind of similar to what people do for things like laser diodes and things like that. All the way on the other end to the nuts and bolts of a fiber draw tower. And, how do we actually we actually do this process and get it to work right, and get great diameter control on the fiber? How do we make the preform even, and have this core cloud interface be really pure, and therefore support really, really good total internal reflection, really, really low attenuation? So there's a whole world of different science that goes into optical fibers, from material science to physics and waveguide simulation, to mechanical electrical engineering to work on the manufacturing equipment, and everything else you can imagine. So for me personally, it's a really, really fun field to be in, because we don't just work on the fiber, but we work on a lot of different fields that all come together to make this fiber a reality.
Thanks. Next question is from Michael. Is the mode pattern in the GRIN multimode fiber less susceptible to movements of the fiber compared to a step index fiber?
Yeah, I don't have a good answer for that one. Graded index fiber is not really something that I've worked on too much, so yeah, not really sure about that one.
Yeah, I wasn't sure about that.
That'd be
either.
something we'd have to look into.
Yeah. In telecom, how is the signal in the fiber modulated to achieve high bandwidth?
There are an incredible number of different strategies to modulate the signal in telecom. Again, I'm not an expert, but I can offer some examples. My knowledge is probably like what they did 20 years ago, like the first couple ideas they had. So one example is, of course, the simplest way to get data through a fiber is you have a light source on one end and you turn it on and off, and on equals a 1 and off equals a 0 in binary code. But you can actually have many light sources of slightly different wavelengths, and each one of those can turn on and off at different times. The fiber, of course, can transmit a wide wavelength range. So, as an example, telecom communications are typically centered at 1550 nanometers, and we can use a device called a WDM, or wavelength division multiplexer. That was one of the examples I had on my fiber devices slide. And this will kind of split out all these different wavelengths in very, very small windows, 1550, 1550.1, 1550.2, or maybe even finer, probably actually a lot finer. And in that way, we can transmit multiple signals through one fiber at the same time. I know there are also some different strategies with the polarization state of the signal that goes in. I think right now the state of the art is something like maybe like 32 or 64 channels per wavelength that a fiber can transmit. It's incredible how much data can go through one fiber. And there's a whole field of building and designing telecom transceivers. And the idea there is it's really expensive to lay fiber on the ocean floor, let's say. But if you can upgrade the boxes at either end to talk to each other through the fiber, and you can increase the data bandwidth, then we can all watch Netflix in higher resolution. Everybody wins.
Sounds good. Netflix is important. On slide 20, at high power, does the optimum placement of the fiber surface with respect to the focus of the laser change? For example, should the focus be outside of the fiber, on the end face of the fiber, or internal to the fiber?
Yeah, so there are a couple different strategies there for high power. And Pat, you might know this one better than me, but I think the focus is slightly behind the end face. For you want to commonly you can focus the laser beam down to a lot smaller than the multimode fiber core diameter. You're not quite worried about the 70% rule. And so if you put it behind, then or even in front, and you have the beam diverge a little bit or be not quite focused at this end face, then you can have the lowest power density possible that still fits inside the fiber's core. And thereby it's like a safer way to work with high power without sacrificing coupling efficiency into the fiber. And to take it a step further, there's even a strategy where we put a glass end cap of core material on the end of the fiber. And that way, that's even bigger. And so you can have an even larger beam entering and a smaller power density and less risk of end face damage.
Yep. Okay, we have time for one more question.
Okay.
How do you inspect for fiber breakage? Is there a tool to precisely locate the position of the crack?
Yeah, there's a couple different strategies for looking for breaks in fibers. And it sometimes comes down to, is the fiber already installed in a data center, in an application, or do you have access to the fiber? The most basic way to do it is with what we'd call like a fault checking light source. And it's as simple as it sounds. Visible laser or visible LED coupled into the fiber, and then inspect along the fiber's length. And if you see a bright spot, that means light's leaking out, which means something is wrong with the fiber. Not just a break, but also maybe some sort of internal defect in the fiber. Things like that. Not that those come up very often, but it is possible. And then a more less straightforward way to look for fiber breaks is what we call an optical time domain reflectometer, or an OTDR. And the idea there is this is a machine that's going to emit a very short pulse of light into the fiber. And it's just connected to one end of a long fiber spool. But with a very sensitive detector, it's going to look for that pulse to come back, to be reflected somewhere in the fiber and come back to the instrument, which is connected to the fiber spool. And not only does it look for that pulse, it looks for intensity, and it times how long it takes for that pulse to get back. Of course, we know the index of the silica glass core, so we know the speed of light in the silica. And so we can actually tell from there, how far into the fiber spool do we have some sort of reflecting thing. And the main thing that was going to reflect is if the fiber is broken, now you get Fresnel reflections at that broken piece of the fiber, at that end face, that probably not very nice end face. And so for that way, we can actually fault check a fiber and look down kilometers and kilometers and kilometers of fiber and detect those breaks in fiber that we can't see with really, really good spatial resolution.